So I'm going to break this problem up into two parts. The first part is going to be making the control system and getting the ideal P and D controllers out of it. And the second part is going to be finding the tracking error, which is something that I'll go over for the first time. So for the control system, it's going to be similar to what we had before. So this is no different than what we've already looked at previously. You have a desired angle, and it's going through a P controller. It's going through the plant, and for the velocity, there's going to be some feedback, and here's the D controller. And then the velocity is going to get integrated to turn into the actual angular displacement, and the actual angular displacement will subtract from the desired angular displacement to get your error signal here. So let's simplify this control system. So after eliminating the first feedback loop, you can see that the model looks a lot cleaner, and this is how we were able to derive this transfer function. We can further reduce the control system by doing the following. So now that we have reduced the block diagram to its simplest form, we can now pick off the components of the transfer function, because this is a second order system, we need to follow the second order transfer function form. So now that we have this in the form of the second order transfer function, we can now pick off the components accordingly. So you can see here that after picking off the values of the transfer function, we now have our P and D controller. So what we're able to do with this is now we have the freedom to change the frequency into whatever we would like. So the perfect P value would be something that the frequency was twice under the resonance frequency. So for simplicity, let's just say that omega n, so the frequency of the system, must equal at least half of the resonant frequency. So when we change these values and we tell the system, hey, you have to be under the resonance frequency by at least 2, by a factor of 2, this tells the P controller what value to be to make this happen. So the new P controller would then be this. So the system would now be the resonance frequency squared times the time constant over 4 times the gain. Likewise, for the D controller, you can specify the zeta, or the critical damping ratio. So we want the critical damping ratio to be a value that's over 1, but this is more flexible and can be controlled by the user, just like the resonance frequency, how you can change that accordingly to change your p-value. So instead of just setting this to a value of 1 for a critically damped system, I'm going to make it generic here and just call this the critical damping ratio, or otherwise known as just having this be set as CR for critical damping ratio. So whatever that may be for your system. It could be 1, it could be 1.1. That's dependent upon what you need your system to be and how you want it to react. So I'm just going to put a CR here for this being the critical damping ratio. Back in my first video, I talked a little bit about the unit functions that you can do to test the signals of your system. I went over 1 over S, which was a unit step function, and I went over 1 over S squared, which is a unit ramp function. I talked about that maybe about 8 minutes into the first video, so if you haven't looked at that, I would look at that right now. So when we say that we want to determine the tracking error, what you want to determine is how your system reacts as time approaches infinity with a unit ramp function going into your system. So you have a 1 over S squared that will go into your system, and you want to calculate small f infinity to know how your system will react with this input over a long period of time. We don't want to do this we don't want to convert the frequency domain into the time domain because we don't have to. It would be a lot longer drawn out process if we had to do something like that. But instead, because we know a couple of techniques, we're able to determine as time goes into infinity as the frequency domain. So here is how you would do that. So what I'm doing here is I'm taking the desired angular displacement and subtracting that from the actual angular displacement. So that's giving me is my error, denoted by the capital E. So because we know that this is the transfer function of the overall system, and that the transfer function, any transfer function, is just its output over its input, we know that we could just as easily represent the actual angular displacement here as the transfer function times the desired angular displacement by switching this to the other side here. So that's why we are left with this, and we can factor out the angular displacement and be left with this. This is something that we can actually calculate now. Our desired angular displacement is going to be the tracking error, or it's going to be the unit ramp function. And we know our transfer function because it's right here. So if we do a little math, we can figure out what the actual error will be. So you can see for our input, we have a unit ramp function, and that is why we've replaced the input are the signal going into the system, which would have been the desired angular displacement. We've replaced that with a 1 over s squared to see how our system would react because of that. So we want to see what our error signal will be as time goes to infinity, which is why we are taking as s approaches 0 and we're multiplying the whole system by s. If you are confused by this, I mentioned how to do this in some of the previous videos. So what we would do here is now cross off all the s's accordingly. So this would go away, these would go away, and you'd be left with this. So as s approaches 0, you'll see that this ends up going away, this goes away, and so does all of this. So you'd be left with 1 plus k_kv over k_kp. It's also worth noting that in this particular case, we wanted to know the tracking error, so you'd use the unit ramp function. However, if you wanted to know the unit step function, you would use, it would be called the static error. And instead of 1 over s squared, it would be just 1 over s. So if you recall earlier in this lecture, you could see that these were the P and D controllers. So now the question asks to be able to put the tracking error in terms of the P and D controllers, where you can put it in terms of the resonance frequency and the critical damping ratio. So they want to know what the error will be with respect to these variables. So this is what it would look like. And from here you can start canceling things out. I forgot to include the resonance frequency over 2 because earlier in the problem I stated that the resonance frequency we were going to put as, or sorry, the undamped natural frequency we're going to put as the resonance frequency divided by 2. I also forgot to, I might have canceled out K instead of KP, but this is supposed to be just K. And this was supposed to be KP because we replaced KP with this value right here. So this originally used to be K times KP, like it was right here. So I replaced KP and I put this there instead. So this would also go away too. So what you would be left with is 4 times the critical damping ratio times the, or over the resonance frequency. And this would be your tracking error. So this is basically saying that with everything that you have in the system right now, you're still going to have some error. And this error is due to, in this case, your critical damping ratio and your resonance frequency. You're always going to have to find a balance between that to reduce the error. But how you would solve the tracking error, or if tracking error does exist, you can always, in this particular case, you can add an I controller, and that would effectively bring the tracking error down to 0. In all cases, you want the error as time reaches infinity to be 0. You never want it to be some remaining value like it is right now. So again, to reiterate, how you would solve this error would be to add a I controller. And also, this would be a good practice to do, a good practice problem. If you, instead of did the tracking error, do the static error, where you do the same exact problem, but you do it with 1 over s. I think you'll see that instead of getting an error here, you would get 0 instead. So I'll leave it to you guys to see if you get that answer, and it should make sense why you get something like that. Because when you have a static error, you are essentially not constantly changing the input. The static error is just a unit step function. So you would have less room for error if you're just going at a constant displacement. So for this particular problem, they're asking you to find the transfer function of z over x. You know transfer functions are equal to the output over the input. So in this case, the output is z and the input is x. So the transfer function must be this block right here. For the next problem, the output is y and the input is x. So you would find the solution for the whole entire block diagram. So these would be your answers to these two questions. So for this question, they want to know the transfer function of y over x when the z is evaluated to be 0. So that means this could be like a disturbance entering into the system. So they're saying that in this particular case, the z will equal 0 so that you can calculate the transfer function of this whole entire system without the disturbance of z. So this is what it would look like. So this is what the answer would be. It's simple, straightforward. All you would do is just the block diagram math without the input of z. For this next case, they want you to do the whole entire system, except in this case, x is now not contributing and z is the one that's entering into the system. So no x, but this time there's z. If we wanted to do something like that, you can consider this junction point blocked off, and this would just be a normal straight line going to the end destination. So if you have something like that, the equivalent block diagram would be equivalent to having this B and C right next to each other. So they would be in series and they would multiply with each other. So this is what the transfer function would look like for this scenario. So here is the equivalent control system for this transfer function. You can see that for this feedback loop that's going back around, you have a plus here, and that means that the denominator of this transfer function is going to be a negative instead of a positive, like what we've normally been doing. And also, as z goes into the system, it becomes a negative sign. So this is why that you have a negative a starting here. It might look a little different because I didn't draw the junction up on the top like where you normally have it right here, but these systems are equivalent. So this would be just the same as if I put this junction on top and fed the system into here, through here. It just might look a little different. So the next question is asking if there are both signals going into the system. So you have both x and both x and z going into the system together, then what is your y? So the answer to this is that it's actually a combination of both part A and part B. It's something called superposition, where you're adding the components. So that would look something like this. So you can see that this is your answer here because, and you might ask yourself, why did I put an x here and why did I put a z here? Well, you're adding up the components of y, and in this case, this is a component of y, and this is the component of y, and you need to add those together. So you need to take the x and put it on the other side, and take the z and put it on the other side of the transfer function. So this is your transfer function, and then this is the x of s, and this is the z of s. So that's why you have the x of s here and the z of s here. The x being the input for when z was equal to 0, and z being the input when x was equal to 0. So the input of your system for the x multiplied by the transfer function of the system of the transfer function when z was not active, and the same side for when x was not active. So this is how you would calculate the component. This is how you'd calculate the output of a system if there was multiple signals going into your control system.